Welcome. In this presentation, we will review clustering using R and the KMeans method. Let's start by defining clustering. In essence, clustering involves grouping similar data points together based on certain features or characteristics. The primary goal is to create clusters or groups where items within a cluster share more similarities with each other than with items in other clusters. Now let's explore some key points that illuminate the significance of clustering. Clustering is often categorized under unsupervised learning. Unlike supervised learning, it doesn't require labeled training data. Instead, clustering algorithms identify patterns and relationships within the data without explicit guidance, allowing for the exploration of inherent structures. Clustering relies on a similarity metric to measure how alike data points are. This metric, often expressed through distance measures like Euclidean distance or cosine similarity, quantifies the similarity or dissimilarity between data points. It's a crucial aspect that guides the clustering process. The applications of clustering are diverse and impactful. Think of it as a versatile tool applicable in customer segmentation, anomaly detection, image segmentation, and recommendation systems. By grouping similar entities, clustering provides insights that drive decision-making in various domains. There's no one-size-fits-all approach in clustering. Different algorithms cater to different scenarios. Whether it's the widely used K-means, the hierarchical clustering for tree-like structures, or the density-based DBS-can, each algorithm has its strengths and weaknesses. The choice depends on the nature of the data and the goals of the analysis. In summary, clustering isn't just a technical concept. It's a powerful tool that empowers us to discover meaningful patterns within datasets. It operates in the realm of the unknown, revealing structures that might otherwise remain hidden. As we navigate the landscape of unsupervised learning and similarity metrics, keep in mind the real-world applications that benefit from clustering's capabilities. From understanding customer behavior to identifying anomalies in data, clustering is a key player in the realm of data analysis. As we continue our exploration into the world of clustering, we now shift our focus to understanding the profound significance of this technique in the realm of data analysis. Let's delve into the key reasons why clustering holds immense value. One of the foremost roles of clustering is its ability to uncover hidden patterns and structures within large data sets. Imagine navigating through vast amounts of data manually. A daunting task, to say the least. Clustering simplifies this process by grouping similar data points together. In doing so, it reveals inherent relationships that might remain elusive through manual analysis alone. This is the power of clustering in unlocking patterns that transcend the limits of human perception. Businesses thrive on informed decision-making, and clustering serves as a valuable ally in this regard. By understanding the characteristics of different clusters, businesses can tailor their strategies to specific customer groups. Take, for instance, customer segmentation. Clustering allows businesses to identify distinct segments of their customer base with shared preferences. Armed with this knowledge, they can fine-tune marketing strategies, product offerings, and customer experiences to cater to the unique needs of each segment. In the vast landscape of data, anomalies often hide in plain sight. Here's where clustering becomes a powerful tool for anomaly detection. By establishing what is considered normal within a cluster, clustering aids in identifying outliers or deviations from the norm. This is especially crucial in areas like fraud detection, where abnormal patterns might indicate fraudulent activities. Clustering empowers us to detect these anomalies swiftly and effectively, enhancing the overall robustness of data analysis. As we navigate through the intricacies of data analysis, keep in mind the transformative impact clustering has in uncovering patterns, supporting decision-making, and enhancing anomaly detection. The next set of compelling reasons why clustering matters profoundly. As we navigate these insights, envision the transformative impact clustering has on making sense of complex data sets. Picture this: large data sets, intricate and overwhelming. This is where clustering steps in as a savior. It allows for the simplification of complex data, making it more manageable. By grouping similar data points together, clustering preserves essential information and insights while reducing the complexity of the dataset. This process of data compression and simplification not only eases the analytical burden, but also retains the core value within the data. In the dynamic realm of marketing, where personalized experiences are paramount, clustering emerges as a strategic ally. By understanding customer segments through clustering, businesses can tailor their marketing efforts to specific groups. This is the essence of targeted campaigns, a key strategy to improve the effectiveness of advertising and promotions. Clustering equips businesses with the knowledge to address the unique preferences and behaviors of distinct customer segments. Resource allocation and optimization are critical considerations in various domains, and clustering plays a pivotal role here. Consider supply chain management, for instance. Clustering helps streamline inventory distribution based on demand patterns within different clusters. This strategic approach ensures that resources are allocated efficiently, minimizing waste and maximizing effectiveness. It's a testament to the practical applications of clustering and optimizing resources for better operational outcomes. At the core of data analysis is the quest for understanding. Clustering serves as a catalyst in this pursuit. By grouping similar data points and uncovering patterns, clustering enhances our understanding of the underlying structure of data. It transforms raw data into meaningful information, fostering a deeper comprehension of the relationships and dynamics within a data set. This improved understanding paves the way for more informed decision-making and strategic insights. As we explore these facets of clustering's significance, remember that it goes beyond just grouping data points. It's about unlocking the potential within data and harnessing it to drive positive outcomes. The essence of a good clustering lies in two key components: intra-cluster distance and inter-cluster distance. Imagine you have a group of objects within the same cluster. The intra-cluster distance is all about how close or similar these objects are to each other. The goal here is to minimize this distance. By doing so, we ensure that objects within the same cluster share common characteristics or features. Think of it as creating tight-knit communities within the data where members are closely related. This minimization of intra-cluster distance enhances the cohesion of clusters, making them more internally consistent. Now let's shift our focus to the space between different clusters. The intercluster distance measures the separation or dissimilarity between distinct clusters. Here, our objective is to maximize this distance. The greater the distance between different clusters, the more distinct and well-defined they become. It's akin to creating boundaries that clearly delineate one group from another. Maximizing intercluster distance helps us avoid overlap, ensuring that each cluster represents a unique set of patterns or characteristics. So, what does this mean in practice? A good clustering is one where, within each cluster, the sum of distances between objects is minimized. Intra-cluster distance, creating cohesive and internally consistent groups. Simultaneously, the distances between different clusters are maximized, inter-cluster distance, establishing clear boundaries and making each cluster distinct. In visual terms, think of it as arranging data points in such a way that objects within a cluster huddle closely together while maintaining ample space between different clusters. This concept is crucial because it guides us in creating clusters that truly capture the underlying structure of the data. It's about finding the right balance. Tight-knit clusters with minimal internal distances and distinct clusters with maximum separation from one another. As we embark on our journey of clustering, keep these principles in mind. They form the foundation for meaningful and effective clustering, allowing us to extract valuable insights from our data. Let's delve deeper into intra-cluster distance and intercluster distance. The first concept, intra-cluster distance, invites us to explore the closeness or similarity between objects within the same cluster. Picture it as a measure of how tightly knit or cohesive a group of objects is. Our primary goal here is to minimize this distance. Why is that important? Well, by minimizing intracluster distance, we ensure that objects within a cluster share common characteristics or features. This cohesion is critical for the meaningful identification of patterns within individual clusters. Think of it as creating clusters where members are not just close in proximity, but are also similar, enhancing the internal consistency of each cluster. Now, let's shift our focus to the space between different clusters, the intercluster distance. This concept involves understanding the separation or dissimilarity between distinct clusters. Our objective here is to maximize this distance. Why does it matter? Maximizing intercluster distance is essential to avoid overlap and establish clear boundaries between clusters. It ensures that each cluster represents a unique set of patterns or characteristics. This separation facilitates the differentiation of diverse patterns present in the dataset. Visualize it as creating distinct territories within your data landscape, each with its own unique identity. In summary, the significance of these concepts lies in finding the right balance. We aim to create clusters where objects within a cluster are closely related, minimizing intra-cluster distance, while ensuring that different clusters are distinct from one another, maximizing intercluster distance. This delicate balance is what makes clustering effective in revealing the underlying structure of the data. As we apply these concepts in practice, keep in mind the broader implications. Minimizing intracluster distance enhances internal consistency, fostering meaningful pattern identification. Maximizing intercluster distance establishes clear boundaries, facilitating the differentiation of diverse patterns within the dataset. Now, let's dive into the world of K-means clustering, one of the most widely used algorithms in the realm of data clustering. Understanding how K-means works is like unlocking a powerful tool for uncovering patterns in our data sets. Before we delve into the algorithm itself, let's address the question, why K-means? In the vast landscape of clustering algorithms, K-means stands out for its simplicity and effectiveness. The fundamental goal of K-means is to improve the intergroup similarity while keeping the groups as far apart from each other as possible. It achieves this by running on distance calculations, a concept that lies at the core of many clustering techniques. At the heart of K-means is the use of Euclidean distance for distance calculations. Now, what is Euclidean distance? It's a measure of the straight-line distance between 2 points in a space. In the context of K-means, this is applied to calculate the distance between data points. The formula for Euclidean distance in two-dimensional space is familiar. However, the beauty of this formula lies in its adaptability. It seamlessly extends to multidimensional spaces as well, accommodating an increase in the number of terms. So, whether we're working in 2D or multidimensional space, Euclidean distance is the metric that K-means relies on for its calculations. You might wonder, what does the K in K-means stand for? It represents the number of clusters into which we want our data to divide. This parameter K is a critical input, as it guides the algorithm in creating the desired number of groups or clusters in our data. In essence, KMeans is about finding the centroids that represent the centers of these clusters. It iteratively refines these centroids until convergence, adjusting them based on the distances between data points. The end result is a partitioning of our data into K distinct clusters, each with its unique set of characteristics. As we embark on our journey with K-means clustering, remember the simplicity in its approach, optimizing group similarity while maximizing the separation between clusters. It's a balance that allows us to reveal meaningful patterns in our data. Now that we've established the fundamentals of K-means clustering, let's take a closer look at the step-by-step process that this powerful algorithm follows to partition our data into distinct clusters. At its core, K-means clustering is a process of divide and conquer, where our goal is to partition our data into K clusters based on certain features. Let's break down the key steps involved. The process begins by defining or initializing the center points of our clusters. These initial centers act as the seeds around which our clusters will form. Next, each data point is assigned to the cluster whose center is closest to it. This assignment is based on the distance calculation, often using Euclidean distance. Each data point finds its home in the cluster whose center it is most similar to. With the initial assignment, we now calculate the centroid of each cluster. The centroid represents the center point of a cluster, and the centers are then moved to these newly calculated positions. After repositioning the centers, each data point is reassigned to the cluster whose center is now closest to it. This realignment ensures that each point is associated with the most fitting cluster based on the updated centers. The process iterates until no data points move between clusters. In each iteration, the centers are adjusted and data points are reassigned. The repetition continues until a stable state is reached, where no further adjustments are needed. This iterative refinement ensures that the algorithm converges to a solution where the clusters are well defined, and each data point resides in the cluster that is the best fit for its characteristics. The K-means clustering process is both intuitive and effective, making it a go-to method for data partitioning and pattern recognition. As we explore the world of K-means clustering, keep in mind this dynamic process of defining clusters, adjusting centers, and refining assignments until we achieve a stable and meaningful partitioning of our data. As we venture further into the realm of K-means clustering, a crucial question arises. What is the best value of K? Determining the optimal number of clusters is a key consideration in ensuring the effectiveness of our clustering results. Let's explore some methods to find the most suitable value for K. One approach is the empirical method, where the number of clusters is approximated as the square root of the total number of data points divided by 2. In mathematical terms, it looks like this. Here, N represents the number of data points in our data set. While this method provides a quick rule of thumb, it's important to note that its accuracy may vary based on the nature of the data. Another widely used technique is the elbow method. This method involves plotting the sum of within-cluster variance against the number of clusters. The turning point, or elbow, in this curve indicates the optimal number of clusters. It's at this point that the addition of more clusters doesn't significantly reduce the within-cluster variance. The elbow method provides a visual cue for choosing the most suitable K value based on the point of diminishing returns. Lastly, we have the cross-validation method, which introduces a level of sophistication by dividing the data set into multiple parts. Here's how it works. Divide the data set into M parts. Use one part for testing the quality of clustering. For any given value of K, repeat this process M times, comparing the overall quality measure with respect to different K values. Identify the number of clusters that best fits the data. This method leverages the power of cross-validation to ensure that our choice of K is robust and holds up across different subsets of the data. In summary, determining the best value of K involves a combination of empirical rules, visual analysis through the elbow method, and the thorough validation provided by cross-validation. Each method brings its unique perspective to help us make an informed decision about the number of clusters that best captures the structure of our data. Let's delve into a powerful technique known as the elbow method, a valuable tool in the world of cluster analysis. The elbow method is designed to help us determine the most appropriate number of clusters in a dataset, providing a visual and intuitive way to interpret and validate the consistency within our clustering results. Imagine you're faced with the challenge of determining the optimal number of clusters for your data. The elbow method comes to the rescue, offering a systematic approach to finding that sweet spot. How does it work? The elbow method involves plotting the sum of within-cluster variance against the number of clusters. Within-cluster variance, also known as inertia, represents how spread out the data points within a cluster are. As you increase the number of clusters, the within-cluster variance typically decreases. However, there's a point where adding more clusters doesn't significantly reduce the variance. The elbow method is about identifying this turning point or elbow in the plot. The point at which the reduction in within-cluster variance starts to diminish is considered the optimal number of clusters. It's the point where adding more clusters doesn't provide much improvement in capturing the structure of the data. The beauty of the elbow method lies in its visual nature. When you plot the within-cluster variance against the number of clusters, the graph often resembles an elbow, hence the name. The elbow is the point where you start to see diminishing returns in terms of reducing variance. Choosing the right number of clusters is crucial for meaningful and interpretable results in clustering. The elbow method adds a layer of objectivity to this decision-making process, allowing us to identify a balance between capturing patterns in the data and avoiding overfitting. In conclusion, the elbow method serves as a guiding light in the often subjective task of determining the optimal number of clusters. It combines quantitative analysis with a visual interpretation, providing a robust approach to enhance the reliability of our clustering results. As we venture deeper into the world of clustering, we now turn our attention to the critical task of evaluating the quality of our clusters. One powerful metric that aids us in this evaluation is the silhouette coefficient, a measure of both cluster cohesion and separation. The silhouette coefficient serves as a quantitative measure of how well each data point fits into its assigned cluster. It takes into account two crucial factors: closeness to intra-cluster. Points considers how close a data point is to other points within the same cluster. The closer the points are, the higher the cohesion within the cluster. Distance from intercluster. Points takes into account how far away a data point is from points in other clusters. This measures the separation between clusters. The silhouette coefficient values range between 1 and 1. Let's break down what these values signify. Negative values, close to 1, indicate that a data point is closer to points in other clusters than to its own cluster. This suggests poor cluster quality and a possible misassignment of the data point. Values around 0 suggest overlapping clusters, where a data point is equally close to points in its own cluster and neighboring clusters. Positive values, close to 1, indicate that a data point is closer to points in its own cluster than to points in other clusters. Higher positive values signify strong cluster cohesion and well-separated clusters. Evaluating clusters is essential for ensuring that our partitioning of data is meaningful and aligns with the underlying structure. The silhouette coefficient provides a concise and informative measure that helps us gauge how well-defined and distinct our clusters are. In summary, the silhouette coefficient is a valuable tool in the toolkit of cluster evaluation. It goes beyond the mere number of clusters and provides a nuanced understanding of the quality of each cluster. As we navigate through the world of clustering, let's keep the silhouette coefficient in mind as a guiding metric for cluster assessment. Now, let's explore how to implement KMeans clustering in the R programming language, a powerful environment for data analysis and statistics. This snippet of code provides a simple guide on how to get started with KMeans in R. The first step is to load the required libraries. In this case, we're using the datasets and charate libraries, which are commonly used for data manipulation and machine learning tasks. Additionally, we check if the NB-SLUST library is installed and install it if needed. NB-CLUST is particularly useful for determining the optimal number of clusters. Datasets provides access to various built-in datasets, which can be handy for testing and practicing clustering algorithms. Charate offers a comprehensive set of tools for training and evaluating predictive models. NB-CLUST aids in the selection of the optimal number of clusters using various methods. Once these libraries are loaded, you're ready to dive into KMeans clustering using your dataset. The subsequent steps would involve loading your dataset, preparing the data, and applying the KMeans algorithm. Remember, R provides a rich ecosystem for data analysis, and integrating KMeans into your workflow allows you to uncover hidden patterns within your datasets. Let's take a practical step and see how to import and prepare data for KMeans clustering in R. The code snippet provided gives us a glimpse into the process of importing and preparing the famous iris dataset for clustering analysis. Here, we're using the built-in iris dataset in R, a classic dataset often employed for testing and practicing various statistical and machine learning techniques. The data function loads the dataset into our R environment. The next step involves preparing the data for KMeans clustering. Here's what's happening in this code. Scale iris, C5. This part scales the numeric variables in the dataset. Scaling is a common pre-processing step that ensures all variables are on a similar scale, preventing certain variables from dominating the clustering process due to their larger magnitude. Data frame. The result is then converted into a data frame for ease of use, head X. This function displays the first few rows of the prepared data, giving us a glimpse into the transformed dataset. Scaling the variables is crucial for KMeans clustering, as the algorithm relies on distance calculations. Ensuring that all variables contribute equally to the clustering process helps in obtaining more reliable and meaningful clusters. Before applying KMeans clustering algorithms, it's always a good practice to inspect the prepared data. The head X command allows us to take a quick look at the structure of our dataset, ensuring that the scaling process has been applied successfully. As you work with real-world datasets, adapting these steps to suit the characteristics of your data is key to obtaining accurate and insightful clustering results. Let's explore a crucial step in the process, determining the optimal number of clusters using the elbow method. The code snippet provided demonstrates how to create and visualize an elbow method plot to make an informed decision about the number of clusters. Here's a breakdown of the code. Wisplot is a custom function designed for the elbow method. It takes the dataset, data, the maximum number of clusters to consider, NC, and a seed for reproducibility, seed, as parameters. The function calculates the within-cluster sum of squares, WES, for each potential number of clusters. It then creates a plot depicting the number of clusters against the within-group's sum of squares. The idea is to identify the elbow, or the point, where the reduction in within-cluster variance starts to diminish. The Wisplot function is applied to our prepared dataset, X, with a maximum of 30 clusters. The resulting plot provides valuable insights into the optimal number of clusters for our K-means algorithm. The elbow method aids in finding the right balance between capturing patterns in the data and avoiding overfitting. The elbow in the plot signifies the point where adding more clusters doesn't provide significant improvement, helping us choose a reasonable number of clusters. As you execute this code, observe the plot that emerges. Look for the point where the within group's sum of squares starts to exhibit diminishing returns. This point is often considered the optimal number of clusters for our dataset. In conclusion, the elbow method plot serves as a valuable guide in making informed decisions about the number of clusters, enhancing the effectiveness of our K-means clustering analysis. Now that we've determined the optimal number of clusters using the elbow method, let's move forward and actually run the K-means clustering algorithm on our prepared dataset. The provided code snippet showcases how to perform K-means clustering in R. Here's what each line of code does. KMeans x3. This line initiates the K-means clustering algorithm. The function KMeans takes the prepared dataset x and the specified number of clusters, in this case 3, as parameters. The result is stored in the variable KMeans. Table iris species, KMeans cluster. This line creates a contingency table comparing the actual species labels from the iris dataset with the cluster assignments obtained from K-means. This table helps us assess the agreement between the true species labels and the clusters assigned by the algorithm. The K-means cluster column in the output represents the cluster assignments generated by the K-means algorithm. The table compares these cluster assignments with the actual species labels from the iris dataset. Assessing the contingency table provides insights into how well the K-means algorithm aligns with the actual species labels. It helps evaluate the accuracy and validity of the clustering results. In conclusion, running the K-means algorithm and examining the results through a contingency table is a crucial step in assessing the performance of the algorithm on real-world datasets. Now that we've executed the K-means clustering algorithm, let's explore the output it provides. The result of the K-means function is a list containing several important pieces of information. Let's delve into the key components of this output. The output of the KMeans function is a list, and among the various components, the most crucial ones are cluster. This is a vector of integers ranging from 1 to the specified number of clusters, K. Each element in this vector corresponds to the cluster to which a data point is allocated. Centers. This component is a matrix representing the cluster centers. It provides the coordinates of the centroids around which the clusters are formed. Tots. The total sum of squares represents the total variance in the dataset. Withins. This is a vector containing the within-cluster sum of squares for each cluster. It quantifies the variability within each cluster. Tot. Withins. The total within-cluster sum of squares is the sum of withins, representing the overall variability within all clusters combined. Betweens, the between-cluster sum of squares is calculated as tots minus tot withins. It represents the variability between different clusters. Size. This component provides the number of points in each cluster, offering insights into the size and distribution of clusters. The cluster vector is particularly useful as it assigns each data point to a specific cluster, allowing us to understand the grouping pattern. The centers matrix gives us the coordinates of the cluster centers, providing a visual representation of the cluster locations in the feature space. The sum of squares components, tots, withins, tot, withins, betweens, helps us assess the overall variance, within cluster variance, and between cluster variance. The size component provides information about the number of points in each cluster, helping us understand the distribution of data across clusters. Now that we've executed the K-means clustering algorithm and explored the components of its output, let's take a closer look at how we can print and examine the results directly in R. The code snippet provided allows us to gain insights into the groupings, cluster centers, and assignments. This simple line of code prints the results of our K-means clustering analysis. Let's break down what we see when we print these results. Groupings. The output provides us with the cluster centers, means, for each group across the variables. These cluster centers represent the central points around which the clusters are formed. Cluster assignments. We also get the cluster assignment for each observation in our data set. This indicates which cluster each data point has been allocated to by the K-means algorithm. Examining the cluster centers helps us understand the characteristics and values that define each cluster. It's a snapshot of the average feature values within each cluster. The cluster assignment for each observation allows us to see how the algorithm has categorized individual data points. This information is crucial for assessing the accuracy and meaningfulness of the clusters. Printing the results is a quick and effective way to gain an overview of the clustering outcomes. It provides us with tangible information that we can use to interpret and validate the results. Now that we've obtained the results from our K-means clustering analysis and printed them, it's time to take our exploration to the next level by visually evaluating the clusters. Visualization allows us to gain a more intuitive understanding of the grouping patterns and the separation between clusters. This code snippet utilizes the FactoExtra library, a powerful tool for visualizing clustering results. Here's what this code does. The visualization typically includes scatter plots or other graphical representations that illustrate the distribution of data points within clusters. Data points within the same cluster are often marked with the same color or symbol, making it easy to identify the boundaries and relationships between clusters. Visualizations help us assess the compactness of clusters and the separation between them, providing insights into the quality of the clustering results. Visualization is a powerful tool for pattern recognition and validation. It allows us to identify any potential issues, such as overlapping clusters or outliers. Visual inspection complements the quantitative assessment provided by the elbow method and other metrics, offering a holistic view of the clustering performance.